Have you ever noticed an ambulance siren seeming to change pitch as it passes by? This familiar wee-wah of the siren is the Doppler effect in action. In general, the Doppler effect is the change in observed frequency, or pitch of a wave when the source and observer move relative to each other. As the ambulance passes, the pitch rises as it approaches and falls as it recedes, a real-world demonstration. This is the Doppler effect. Waves telling us about motion. We'll unpack why this happens for sound and all kinds of waves. First, the basic picture. Moving sources change the spacing of wave crests. The Doppler effect. Waves in motion. Now let's watch a moving source and see the wave fronts change. This simple animation will make the math and physics clear. Imagine a source emitting waves at a constant frequency, f sub 0. If the source moves, each successive crest is emitted from a shifted location. Crests bunch up in front and spread out behind. Shorter wavelength means higher frequency reaches the observer. Longer wavelength means lower frequency. For sound in a medium, the compact formula is f_obs equals f_src times v plus or minus v_obs over v minus or plus v_src, with signs chosen so moving toward gives plus. If the source moves toward a stationary observer at speed v_s, f_obs equals f_src times v over v minus v_s, so observed frequency is higher. If the observer moves toward a stationary source at speed v_o, f_obs equals f_src times v plus v_o over v, also higher frequency. For light, which needs no medium, we must include relativity. The relativistic Doppler formula along the line of sight uses factors of 1 plus or minus v over c. Approaching gives Blueshift, receding gives Redshift. Same idea, different details. Waves tell us the motion whether it's sound or light. Now let's see everyday sounds and technologies that use Doppler. You hear Doppler shifts in day-to-day life. Whenever a siren or horn moves past you, passing trains and vehicles show the same effect. Higher pitch when approaching, lower as they recede. A siren's pitch is noticeably higher just before it passes, then drops abruptly. Even airplanes produce Doppler shifts you can sometimes hear or measure on radio. Moving source, stationary listener. Approaching source compresses crests so you hear higher pitch. Stationary source, moving listener. Run toward a siren and you encounter more crests per second. Pitch rises. Combined motion. If both move, velocities combine in the Doppler formula, altering the shift. You can try this yourself. Ring a bell on a moving train and listen from the platform. The faster the relative speed, the more pronounced the pitch shift. Next, using Doppler for measuring speed, radar. Police radar guns are Doppler radar devices that measure speed by detecting frequency shifts of reflected radio waves. They emit radio waves and listen for the reflected signal. Approaching objects return slightly higher frequency. For radar, the change in frequency delta F is roughly proportional to object speed. The radar computes speed from that shift. Sports speed guns use the same Doppler principle to measure pitch or serve speed. Meteorologists use Doppler radar to map wind velocity inside storms. Shifts tell us motion toward or away. Different wavelengths, same physics. Doppler shifts measure velocity across many systems. From roads to storms, Doppler gives velocities, and onto the stars. Any reflected wave carries motion information through Doppler. Now how does this apply to light and the universe? Light waves obey the Doppler effect too. Motion shifts their wavelength to red or blue. Astronomers compare observed spectral line positions to laboratory wavelengths to measure velocity along the line of sight. Edwin Hubble found in 1929 that nearly all distant galaxies are redshifted, implying cosmic expansion. The greater the redshift, the faster a galaxy recedes, a cornerstone of modern cosmology. By measuring shifts of known spectral lines, astronomers infer motion, rotation, and even exoplanets via tiny periodic Doppler shifts. For example, the Andromeda galaxy is blue-shifted toward us, while most other galaxies are red-shifted away. At high speeds near light speed, relativity refines the Doppler formula and explains cosmological redshifts precisely. Doppler shifts of light reveal the motions of stars, galaxies, and the expansion of the universe. From the largest scales to the smallest, Doppler tells us about motion. Next, Doppler in medicine, ultrasound imaging. In medicine, Doppler ultrasound helps us see blood flow inside the body. The device emits high-frequency sound and listens for echoes off moving blood cells. Moving cells shift the echo frequency slightly. Color Doppler converts shifts into colored flow maps showing speed and direction. The machine calculates speed from the detected frequency shift to assess circulation and detect abnormalities. Clinicians use Doppler to monitor fetal circulation and cardiac function. Doppler detects stenoses or clots by measuring abnormal flow velocities. The same Doppler physics used for sirens and radar helps save lives. A few intuitive analogies make the idea even clearer. Imagine standing on a dock watching regular wave crests pass, each crest at steady intervals. If the boat moves with the waves, you encounter crests less often. Waves seem stretched. Move against the waves and crests bunch up. You hit them more often, analogous to higher pitch when moving toward a sound. Or imagine rain hitting a moving car. The front meets drops more rapidly when moving forward. Run toward someone clapping and you hear claps faster. Run away and they slow. The same idea as Doppler. Key principle, closing motion. Crests pile up, higher frequency, receding. Crests spread, lower frequency. Doppler's original experiments even placed musicians on moving trains to hear the shift. Let's do one step-by-step calculation to make the numbers concrete. Example. A train horn emits a 500 Hz tone. The train approaches at 30 meters per second. Speed of sound is 340 meters per second. Use the moving source formula. F_OBs equals F_SRC times V over V minus V_S. Plugging in values, F_OBs equals 500 times 340 divided by 340 minus 30. That yields about 546 Hz, higher than the source. After the train passes and recedes, denominator is 340 plus 30. Recomputing gives about 459 Hz, noticeably lower, matching what you hear. For low speeds, the fractional change df over f is approximately v_rel over v, a handy estimate. Try this yourself with different speeds and source frequencies. You'll see the same pattern. If both move, plug both speeds into the full formula and compute the combined effect. Next, the people and history behind the discovery and why Doppler matters today. Christian Doppler predicted this wave shift effect in 1842. Buys Ballot and others tested the idea with musicians on moving trains, confirming the pitch shifts. Since then, Doppler has been found everywhere, from radar guns and meteorology to medical imaging and astronomy, law enforcement and speed detection, weather forecasting and storm tracking, medical imaging and blood flow diagnostics, astronomy, measuring star motions and finding planets. Doppler shifts underpin navigation, diagnostics, and our understanding of the cosmos. So next time you hear a passing siren or observe a red star in the sky, remember, waves never lie about motion. References and further reading are in the description. Thanks for watching. Subscribe for more physics explainer videos. See you next time.